So what is the marginal product to capital at these values of k and L? What is partial q, partial k? Well, here's our production function. So who can tell me what this partial derivative is? Partial q, partial k. Marginal product to capital. Anybody? Don't be shy. How? It'll be 0.5 times k to the what power? Negative 0.5, right. We're just using the power function rule. Times L to the 0.5. Don't forget to include that L to the 0.5. See, the trick when you're calculating partial q, partial k, the trick is just to treat L as if it were constant. Okay. When you take and evaluate partial q, partial L, then you're treating k as a constant. Okay. And if we evaluate this partial derivative for these values of k and L, what do we get? We get 0.5, 100 to the square root is 10. And this you could bring down in the denominator. Square root of 64 is 8. So this will be 5/8. Okay. And let's see, if we can convert that to decimal form, 5/8 is what? What? Point? Thank you. Okay. Now, if we wanted to show this in a graph, and we wanted to make things simple, we would say, okay, let's let L be 100. Okay, and now let's measure K on the vertical or on the horizontal axis. We could let L be 100, fix it, L at 100. Measure K on the horizontal axis and Q out here. Now our function would become, if L is 100, we fix that, it would be Q equals 10 K to the 0.5. And it would look very similar to our other graph we had before. Look like this. And now if we look at K equals 64, be right here. We know our output from before is 80. Now we look at the slope of this tangent line right here. The slope of that tangent line is what? Jay, what will the slope of this tangent line be? Yeah, 0.65. Okay, so that would be the geometrical interpretation of partial q, partial k. Okay. All right. See, the same ideas we learned for the case where y is a function of x can be applied with proper modification to this more complicated case.